Today we're going to talk about JET, okay, Hazelcast JET. That's a new product that we launched, and my talk and Greg's talk, there are some common things that we will talk, for the ones that have been there, but mostly, I want to talk about the Java util stream more specific, and how we took that and how we ported Hazelcast into that, and etc. Okay, so question to you guys. I like questions. So let's assume you have a map, okay? Just any map, Java map, and for the sake of argument, let's say the content of a map is where a key is a long, it's the let's say line ID, and then the value is a string. It's a line, okay? And let's say we do want to split this with that character, and then we do want to do a word count. How would you do that? So we have a hash map, right? And or any map. I mean, it could be concurrent map as well. And we want to do a word count. So what would you do? How would you do that? Normal iterator, yeah. So I mean, something like this, right? So what you want to do is you want to iterate through all the entries in this map, right? Which is a lines. You're not interested in the line number. That's not interesting for us. But line itself is interesting. We will split line, right, itself, and we'll get a lot of words. And then what we will do, we'll store those words into a different map, right? In this case, we call it a counts map, where the key is the word itself, and then we do some computation there, where we say, if it's empty, start with 1, and then, when you merge it, apply +1, as more collisions happen, right? So automatically, as this loop goes through, you will end up with a map where key is the words and the value is the count, right? So that's what we want. Now, question to you, what is bad about this one? Like, why this isn't really a good way of doing a count? It is single-threaded, very good. How would you do multiple-threaded? Say it again? Okay.
Streaming might be, for the huge data, streaming might be a problem, like it's overhead or counting line by line. It might be a better approach.
Right. That could be, yeah, but right. So we have to do that, right? So because this is not declarative, this is where we basically tell computer how literally do it. If we want to change this to do, to be parallel, as you said, we need to somehow figure out how to divide this, right? First thing, of course, this map needs to be a concurrent map. It can't be a hash map, right? We need to ensure that if multiple threads is going to, work on it. And then somehow by key or whatever, we have to divide the task, so that they can work. Now, of course, this isn't a one-to-one mapping here. We don't take a record and map that to something else. We basically take a key and value, and at the end of the day, the content in the value becomes a key, and the value becomes totally something else. So we need to make sure that when we do multiple processing, somehow we do things right. But a better way would be with the Java 8 streams, actually use the stream API that they provide, right? And basically say, source, entry set, stream. Now, notice that this is actually a declarative way of. So we're not really telling computer how, or JVM how to do it, right? We're just telling what needs to be done. What needs to be done is take a stream, right? In this case, it's going to be entries in a map. That's your items in the stream. And first, you transform the entry object, right? This is the map entry object into just the value. So that becomes the stream, transforms to the stream of values, right? Which is a string, a line, in our word. And then we do a flat map, right? How many of you know what a flat map is, or what flat map does? Okay, so a flat map is basically where you take one item and you map it into many items, right? A map operation there, that's a one-to-one. So imagine a stream of map entries. What is a map entry? It's a key value, right? Key value pair. So when we map it, it's one-to-one. So we take the first line, let's say it's key is 1 and line is whatever, right? Whatever is in our book or whatever we are counting. You take that and you map it to the value only. So you basically get rid of the map entry object, right? You take only the value as your stream item, right? And then from that value, which is a multiple words, right? You do a flat map by parsing those values, right? Splitting them into many words. So suddenly, if, stream, it's actually static. So let's assume if we had 10 items in my map, right? 10 entries. And for the sake of argument, let's say if each of them had 2 words, right, in it. And after flat map, how many items will I end up with in my stream? 20, right? So I'll end up with 20. So basically that flat map allows me to take X number of, items as from source to map it to Y, right? Which can be different from X. Whereas map is one-to-one. So by flat map, basically now I have a stream of words. That's it, right? One word next to another word. That's all I have after this line, right? And then I could collect. And what does collect do? Collect is basically a reduce operation. It says, okay, now I have a bunch of words in a stream. I want to reduce them, okay? How am I going to reduce them? So, this is all Java 8. So you say, reduce them to a map, okay? But how you're going to do it, first you provide a key mapper. So, in this map, I need to have a key. So what is that key going to be? You have to tell, Java. So I say that whatever the word is in this stream, take that as a key, right? The first lambda expression tells me that. If the stream item is W, take W as a key, right? The second one is my value mapper, right? It's the initial value. What is it? Just put 1, right? And the last parameter that I'm passing is merge operation. It says, as I am mapping, taking, as the stream of words is coming, I take the first word, I put that into map, right, using that key extractor, and I put value as a 1. But if a collision will happen, if I find another word, what I do, it says, take the existing value, left is that, and they take the new value, which is going to be 1, right, that's my original value of that item, and then count them and, merge them back. So as the stream is coming, right, as I'm collecting words on my stream, at the result it will be a map where a key is a string and the value is long. But the beauty is, again, so far I'm just declaring what I want, right? I just say that, I want you to have a stream, I want you to do a flat map on that stream, and then I want you to collect it. But I'm not really telling JVM how to do that, right? It's all about the JVM's implementation and how it's going to decide what to do it. Now, we talked about how we can parallelize it, right? So how can I parallelize this really easily? Say it again. Actually, this is not going to, well, there are going to be multiple threads here. They're going to be main thread, and the collect probably is going to happen on a different thread. But unless we tell JVM, this is going to happen on a single thread still, right? JVM doesn't know that it can do it on a multiple thread. To do this on a multiple thread, you need to have, when you do a dot stream, you actually can also do dot parallel stream. And when you do parallel stream, now then it's able to parallelize it, okay? Again, we as a Java developers, we don't care how JVM does it. It is doing it, right? So that's the beauty. Now, some of you guys know Hazelcast, and the rest of you know what in-memory data grid is. In-memory data grids are, there are many things, but the fundamental is it's the distributed map, right? So, kind of seeing what Java 8, instead of writing how to do it, where the Java 8 allows you to just tell what to do, right? We said, then just like, doing parallel stream here, can we make this, like a distributed stream, right? Can I have a distributed stream? Again, similar to this, I'll just declare what needs to be done, and the framework, whatever you use, will figure out how to distribute this, how to make, locality and how to make efficiently, and all that stuff, right? All that things that ideally you don't want to think about, and you want the framework to take care of it. So how would you do that? Anyone done it before? Okay. Well, you could, what we did, we created this product called JET, and this is how you can do this thing, this exact thing with JET, okay? To do the distributed streams. And now, you could, for those of you who knows Hazelcast, this source here, this source is a map, right? Those of you who know what a Hazelcast map is, it is a map. So what is wrong passing that Hazelcast map into that source and the rest the same and expect it to work distributed? Like, why wouldn't that work? Like, what do you guys think? Why wouldn't that work? Or what is wrong with just passing normal Hazelcast map, which is a distributed map, instead of this, local map, whatever that is? Why do you think that wouldn't work? Or why is it a bad idea? Yep. JVM would know about it, but the answer is actually, see, we need to get, now map isn't a stream, right? Map itself is not a stream. Collections are a stream. You can have a stream out of a collection. Now, for me to take a map and get a collection out of it, I need to do like map.entrySet, which will give me a collection of map entries, key value pairs. Or in this example, I could even do like map.values, which would give me, I didn't have to do this map operation, which converts from key value to value only. I could just say source.values, which would give me a collection of values, and then I could do stream, right? But in all those cases, the values, JVM doesn't know that this is a distributed stream. The moment you call values, it will actually collect all the values in your distributed map to this JVM, and that stream is going to be local Java stream, like local stream. So there's nothing distributed about that. And there's no magic for you to, for it to think that it's distributed. I mean, that's basic Java, so we can't override it. So values, there's a meaning of values, right? It will give you all the values in your object. So, alternative could be like we override the values and, we kind of implement as a proxy as you iterate. We don't give, we don't bring all the values right away to you. You have to iterate, and every time you iterate, it goes to the distributed map and gets one by one. But that kind of defeats the purpose, so we haven't done it. But instead, we basically created a JET framework, okay? Now, JET embeds Hazelcast in it. Again, for those of you who knows Hazelcast, who played with Hazelcast, we made Hazelcast to be very simple. It's single jar file. You can distribute it. You can embed Hazelcast in your application, or you can have it in client server mode. It's very easy to work with. And a lot of other products actually embed Hazelcast, like Vertex does that, Neo4j embeds that. A bunch of other open source projects out there uses Hazelcast, embeds them. So we said, given the foundation of, we already have the distributed system foundation, let's build this on top of Hazelcast. So, and now notice that we are getting the map. It's actually it's a proxy to the same Hazelcast map, but it has a different interface, overloaded interface. So we basically take this same map, let's say from JET, which gives us a iStream map. Now, of course, this is a little bit hackier, where we said now this stream map, it has now a method called stream. Now, normal IMAP doesn't have that method, right? You have to get a collection to get the stream. But, that's the hack where we did, okay, let's introduce a stream method to this interface, which gives you a distributed stream, basically. And then, now the rest, it's the same, right? But the implementation is now distributed. And it gives you the key value pairs, the map entry, automatically as a stream items. And if you notice, and one more thing changes there, is going back. This toMap is a reduce operation. It's a function, right, that we have to send. Now, right now, this function is applied in this local JVM, right? And everything is good. We are happy with that. But if we want to make this distributed, we want this function to be applied on the server side, where the data is, right? Instead of bringing the data to this JVM and processing it here, that's not good, right? That's something we want to avoid. What we do, we basically send the operation to the server, to where the data is, and allow it to collect the results over there, right? And of course, there's going to be some data movement. I'll talk about it a little bit, but this all needs to happen on the server side. For this to happen on the server side, what does this function needs to be able to do? What do I have to be able to do with that function so that I can execute on the server side? Who can tell me that? Some keys will be there, and I'm going to use them. I'm going to, kind of compute over them. But first, this function needs to be serializable, right? I need to be able to send it over there and make it serializable. So again, here's a little bit of a hack here. What we did, we basically created a distributed version of all the collectors that JVM had. So instead of a distributed a collector to map, now we have a distributed collectors. And in this case, of course, I'm doing a little bit smarter. Instead of bringing the result map to this JVM, I actually reduce it to an IMAP. IMAP is a reference to Hazelcast map. So what happens is the data is, sharded and partitioned and distributed across the JVMs. I have my mappers and flat map and collect, which ends up on the server side, executed there, and the result automatically goes into the distributed map. Again, whoever JVM that calls this doesn't receive any data. Everything happens on the server side, and the result is readily stored in Hazelcast maps, and you can compute that. You can take it. So with this one, basically, you can have your data in a, again, stored in a distributed map, right? It's fast, it's in memory, it's low latency, you have high throughput, and now you want to do some computation over it, like you want to reduce it, you want to group by it. In this case, again, it's MapReduce, right? Whatever Hadoop world, whatever you want to do with that, you can do on the server side and store the result again in memory on a different map, ready for you to consume. You could easily do normal collect to map to receive the result on this JVM. But again, in a very large world, in a big data world, you don't want to do that. You want the data stored again on Hazelcast so that you can use it. So, yes.
How big size that map will work properly?
How big map can be? And, terabytes of data. It can be running on 10 machines, each machine having 100 gigabyte of memory. And it can be as big as you want. It's linearly scalable. I mean, all in-memory data grids has distributed hash table, which is linearly scalable by design. So you can really grow this as big as you want. And now, what is JET? I mean, of course, I've been talking about it. It's basically a fault tolerant. In the final version, JET 0.5, we implemented the fault tolerance, where a submitted job, you can restart it, and if it fails, it will have snapshots, it will start again. It's Apache license, it's open source, so, feel free to go and use it, anytime you want. It's distributed data processing engine. So in-memory data grids, you could say that in-memory data grids are also distributed processing or compute engines, and like we do say Hazelcast is, but JET is more advanced version of that. It gives you much more computational power. It allows you to do much more interesting stuff that, again, we'll talk about it. That is built on top of Hazelcast and uses a direct acyclic graph model. Okay, how many of you know what a DAG is, or what a direct acyclic graph model is? Okay, good. So this is what a DAG is, basically. I mean, it's actually a generalized, or MapReduce is a specific version of a DAG process. So where you have in our example, actually, what we did, we had some data, we mapped it to something, and then we reduced it. That was a MapReduce that we did. But DAG is basically a more, well, probably complex MapReduce isn't the right term, but it's a more generic, way of doing any type of processing, and where you actually define the process as a data flow, right? If you notice, the Java 8 streams is a DAG. Actually, forget about Hazelcast. The Java 8 stream in the JVM is a DAG. And other popular ones are Spark, Flink, Apache Tez, Storm. If you guys have used any of these are very popular. And again, actually Hadoop MapReduce itself is a very specific version of DAG. Now Hazelcast and the DAG model actually supports both batch processing and stream processing. So, like, if you look into the Spark, it's a mainly batch processing. Again, can be done with a DAG model. A MapReduce or Java 8 streams or Flink. Sorry, I'm taking it back. Java 8 streams is also actually, unlike the name streams, it's actually again batch because the data source is finite. And then the Flink, for example, where it's a good stream engine, is also can be DAG based. On this example graph, what we see is there's two sources A and G. A and B is does split into two different vertices, and then the result of that D joins with G, and all that things, and at the end of the F is your sink, basically. F is where all the stream goes as a result, right? So in reality, what we did, again, a DAG is where we have vertices and edges. Vertices are the processes, and the edges is how you link one process to another process so that it can execute it. So in reality, here's what actually happened in our code, in our Java 8 distributed word count example. Underlined behind the scenes, JET actually created this DAG. Okay, it prints this out as well, so you can kind of see and analyze it. First node is, or first vertex is, read map from a source, right? In this case, it was a Hazelcast map, which we named it. And then it transforms it. That's the map operation that we did, right? And then the flat map operation again. And then it does a merge local. That's the compute operation that we did. Now, in a distributed world, you actually want to you can do the compute first locally, and then you can merge them from other nodes as well. And I'll have a picture to show that. So so that compute operation that we did, or the reduce operation that we did, actually it has two steps. Once we do it locally, reduce the local data, and then we do the global reduce, which is reducing all the data. And that's obviously is an optimization. And then we link the edges, and as you see, the first merge local, actually it is partitioned, which means that while we do on one node event, we can, just like we talked about doing it on multiple threads, remember? So JET does it on multiple threads. That's why it's called partitioned. So it does the first reduce on multiple threads, but on local machine. But then the merge distributed again does on multiple threads, but distributedly, meaning that it combines all the results from all the machines to one place. And as a picture, here's what it looks like. So your source, because it's a Hazelcast map, it's already partitioned onto multiple nodes, right? In this example, let's say 2 nodes. So just for the sake of simplicity, let's say we have 100 line items on our map. So 50 of them on the node 1 and then another 50 on the node 2. And then we do token. Let's just say 5 threads. So 10 words is tokenized by the first thread, and then another 10 on each thread. And then the result where we tokenize them now we need to for the same words, remember we were merging. Now we need to do a reduce operation or accumulate operation. As you see, now we do them locally. But of course, now multiple threads interact with each other. So a result of this thread is sent to result of the other thread so that we can join them. But what is the key here? It's the word is the key, right? As we merge them, now the word becomes the key. That's how they end up at the same place. But first, again, as you see here, we do it locally. And then as the second step, The second combine operation is actually, again, it's a same accumulate operation, but it's a distributed, where we combine all the locally accumulated results into one large group. Again, the key is word itself is the key here. That's how we determine, which node we have to send it and where we have to combine all of it, so that you don't end up, counting the same word in two different places, right? We want them to eventually merge to the same place to have an accurate result. And then sync is to another IMAP, right? This could be anything, but in that example, we're syncing it to another IMAP. Okay. So why we did that? Yes?
Question. How is it different from a simple MapReduce algorithm? Like in simple MapReduce also you just do a word count from different line and on the basis of word as a key. I'm trying to understand the DAG, like how is it making any difference?
Well, a MapReduce is a DAG, right? A MapReduce is a DAG. DAG is just more generic MapReduce, I would say, where you can have, this one is a simple. It had one mapper and one reducer, but you could really have, different vertices doing multiple reduces, and you can just make this really large and have a more. Again, I mean, probably you can try to do them with a MapReduce as well, but the DAG is just a generic term, and where you can, create data flows as complex as you want, and it's easier or simpler definition, I would say, than a MapReduce. And yeah, and we all know that, like in the Hadoop world, even Spark became popular because writing MapReduce itself, was hard, and eventually people moved to something like Spark, which is a simpler way of doing the same thing. So it is a MapReduce. So what we did here is a MapReduce. It's not anything different. But why we did that with a JET, like why we have this DAG engine that we built, because we wanted to be really fast. We have experience as a Hazelcast company to build in-memory solutions that are really fast, that has a extremely performant network layer, how to merge the data, how to partition the data, how to move the process around and how to compute that, and also to use the localization and optimize the threads and all that stuff. And I don't have performance numbers here, but in his own presentation, Greg shared some numbers, and there's also some on our website, jet.hazelcast.org. It's much faster than Spark, much faster than Flink, and both for batching and streaming. And we also wanted to combine both batch and stream. Like Spark is a batching framework. Their streaming is micro-batching. So they're kind of trying to simulate streaming with micro-batching. The downside of that is the latency between those windows is too large for very real-time processes. So Flink is a good streaming engine, but it doesn't do batching as well. So we want to build something that can do both. And also, Hazelcast itself is known to be using the stuff that Java gives to us. So we have Java data structures. Hazelcast is a distributed implementation of those data structures. We had map, we had queue, we had executor service, we have. And with JET, we said, okay, can we make use of this Java 8 streams, which is a declarative way, or which is one way of writing a DAG? Can we make use of that? So, and we basically, made use of it. And of course, by having Hazelcast inside, it get a lot of power on its own. And we are basically unifying the IMDG features with the fast processing features, so that we can do really some awesome stuff. And I'll have some code to show that. This is a little bit of a history and some properties of JET. We started in 2015. It was an experiment we did. This year in February, we released the first beta version. 0.4 is out. We are actually about to finalize 0.5. All the examples that I'm going to run is based on 0.5. It requires JDK 8, obviously. We talked about Java 8 Stream API here. And yeah. And in terms of the use cases, This is how we envision this to be used. You might say, why would I need that? Basically, you take any source, be it a streaming source or a batching source. A batching source can be a Hazelcast map or a database or a file system. A streaming source could be Kafka, Socket, or anything, or some IoT devices again that you collect through Socket and through network. And then you ingest it to this DAG engine. You process it, right? You convert it just like we did. Stream of words is coming and we are counting them. Imagine this to be a trading platform as the transactions are coming, or I like to use Strava, for example. I don't know if you guys know it. It's an app for runners or bikers where, real time you can see other people running the same course with you. So as the data is coming, your GPS data, I can calculate your pace in the last mile, your average, and kind of all those windowing, streaming stuff that you may want to do with it. And then the output could be anything. Again, could be database, it could be Hazelcast, just our word count example, or it could be some sort of a aggregator tool. Maybe you want to analyze, or some IoT device where you want to push the result. Stuff like that. And another thing is a advantage is, as your data comes, you may want to enrich it using, again, this JET will allow you to enrich the data as the stream of data is coming. One vertices could be some sort of maybe it might be in your cache in Hazelcast, or it might be in a database. So you merge multiple streams. JET allows you to do that as well. It don't have to be single source. It can be multiple sources where you merge them together. So now JET has 3 actually APIs. And the core is what we call DAG API. This is really low level where, remember we talked about vertices and edges and, all that stuff, how to join them. That's basically a, imperative API where you tell really how to do that. Okay, how to join them, how to vertices and how many threads there, how to, whether it's partitioned or local or distributed. It is very powerful, but it's a little bit harder. I mean, you may want to do it, for maybe specific projects, but we're not planning that to be used, day to day by a average developer to build systems. So that's a little bit hard. First, we actually implemented the Java Util Stream API, and it is, again, declarative API, but it has the map, flat map, filter, limit, that type of operations it allows you to do. It has aggregations, and it doesn't have joins, so you can't really join multiple sources. And it's a good for, this is a irony, I think, with the Java 8 streams, actually. The term called streams, but it's not actually a streaming API. It's a batching API. It's suitable for batching. It doesn't have any concepts of windowing or, tumbling windows or any of that concept. It's a really good batching framework. And so that's why it's good for batches, but it's not really good for real-time streams where the data, doesn't end, right? There's no end for data. That's not a good way of it. And as a matter of fact, if Java 8 streams cannot know what the size of your collection is, even if you do the parallel streams, it's going to still use a single thread because it doesn't really know, how much data is going to be there and how to distribute that. So there are some downsides of it. So recently, we start to work on something called Pipeline API. It's inspired by, again, Java 8 streams. It's the similar concept, looks like the same, but it's designed both for batches and streams. So it has much richer control, functionality. It allows you to do joins and etc. So Stream API allows you to basically, do functional style, declarative operations. And you can do these on top of a Hazelcast map or list or Hazelcast JET API. And actually, in addition to that, we implemented it for Hadoop as well. So if you have data on HDFS, we can convert that into Java 8 distributed stream. So you use the same Java 8, map and flat map operations on top of that. So not just the source. your source doesn't have to be Hazelcast. And we took care of the serialization by creating serializable versions of the interfaces. And internal, of course, it's converted to a DAG, and it's strictly for batching. And this is a, like I said, you can do it from HDFS as well. So using, again, Java 8 Stream API, this is how you could do the same word count, assuming it's not in Hazelcast, but let's say it's in HDFS. A key here is this a job config, which tells you where the file is, and what is your input type, what is your output type. I didn't put it over here, but that put aside, we have a specific processor for HDFS, where if you do distribute stream.from source, it actually returns you the same stream interface. So then on top of that, you can do flat map, you can do map, and all the rest is basically the same. And then we have and the pipeline API is again kind of similar. It is a it's a DSL basically, which is put through a planner and also converts to the DAG. It has extra things like join, co-group, group by, and we envision this to be a good API to start with JET. And an example of the same word count is, you'll find it to be similar. As I said, it's very highly inspired by Java 8 streams because, a lot of people are Java developers, and sooner or later, people are going to learn how to use Java 8 streams in their day-to-day life. And that's how the word count, will look like if you use pipeline API. Again, it's the, you do, instead of JET get map, you do, source.read map. You provide a, Hazelcast map in this case. You do the mapping, you do flat map. And instead of collect, we have a specific group by method, which we, again, pass a counting method, which, does the same thing. Group by counting how many words are there. And then a specific method to drain it to. And you can have different type of sinks there. In this example, it's a map. You can have list, or you could have other sources as well. And you execute that through JET as a high-level API. And as I said, these could be your input and output. Map, list, HDFS, Kafka for streaming, socket for streaming, file for batching, and even for IMAP, we in Hazelcast 3.9 we implemented event journals. So for those of you who had maybe you've used map, anyone here used any map listeners like in Hazelcast or other tools? So it's basically events where you receive them. Now imagine a stream of events. So we call it journal. So now Hazelcast exposes that, and using that you can actually build a streaming application, which as the events come, you react on it and do some operations. So you can kind of build a stream API. Now, obviously, the difference between a batch operation and a stream operation is that you submit a batch operation, it executes, and it ends, right? There's end-to-end. But with the stream API, it's continuously running, and it's like application service, I like to think. So let's do some demo here. Hopefully with this, I can have it work. What's happening is because of the projector, I cannot mirror them, so I don't see this on my laptop. And navigate it a bit hard. So I created this class that I use. I have a couple of imports here. I have HDFS files, JET HDFS project, JET Kafka project, and some Kafka dependencies. I've all imported them into my Maven. And let's look into this. So this is your iterative code, right? Remember I showed you the very first time. So a hash map. Let's say we fill it with some entries. Let's look into it. It's really simple. Just puts 3 lines, right? And I want to count them. And the rest is the same code. So counts, twice iterate through it, and the print results. Let me just execute it once just to see how it looks like, because the rest will be similar but not local, of course. Not this way. So Okay. I don't need this either. Okay, so basically there was 3 maps, 3 lines in my map, and Lorem appeared 3 times and Ipsum 2 times, and that's a different map I print out. So quite simple enough. And then, of course, similarly, we have the or Java 8 version or Lambda version of it over here, which exact same code. Over there does the collect and prints the results. It's going to be the same thing. I'm not going to run it. And then let me see. Now let's run the distributed version just to see what it looks like. So the distributed implementation I have takes a either name of the map, source map, or the map itself. And over here I get the map from JET. I call this one. Here, if this map is empty, I again call the same exact method, fill map. Notice that this interface is the same, right? The stream map here has the same interface as the Java map, so I can do it. And then the rest is again same. Notice this is IMAP, not 2map, so it's coming from a different class file, and I pass the name of the distributed map that I want the results to be collected into, right? And I pass the same Lambda function, and I print the results. So let me execute this. So, of course, now it's going to start a JET, right? Because we need to have the data distributedly. And let's see what is happening here. First, because Hazelcast is embedded in JET, and JET uses Hazelcast, again, for those of you who used Hazelcast, this output, not this one, but some of these outputs, you'll find similar because it's Hazelcast starting inside JET. And it prints the size of the member and cluster, and these are some new parameters that we added in the latest 3.9 version. And see, this is the vertex that it generates automatically. And basically, it executed the word count for me, and here's the output that was exact same. Of course, this is an extremely small map, and I don't need any distributed functionality for this. But remember I said there was a way of reading from HDFS. So let's see what I can do with that. Now I can do a couple of things here. First, I could actually now. Sometimes we receive, like for Hazelcast users, sometimes we hear things like, hey, I want to dump all the things that's in Hazelcast to a file system, right? How can I do that? Well, you can do it. You can write a code that iterates through it, or maybe you can have maybe a distributed executor service that you can send to every node, and they go through the local data and dump it somewhere else. But it's relatively challenging task to do. But let's see how easy it is with this one. So here is, let's assume it's the same exact map, okay? But instead of doing a word count, all I want to do is transform the content of it and write to a different map, like have a copy of that map, okay? But transform. And of course, you can imagine, you can go as wild as you want, how you want to transform it. But to keep things simple, I just do basically I take this source map, which is the key value entries, right? I map it to this entries to a tuple where the key is the same, but the value is to uppercase. Basically, I create a different key value out of this. And then I collect the results as is, like I take the key as a key and I take the value as a value, and no merge operation, to a different IMAP that I call result, and then I print that. So if I execute this, you will see that. So this was my original, right? And this is my copied map that I printed. So you can do limit here, you can do other type of reductions here. But as you see, copying a map became extremely simple. Now honestly, using this local map that has only 3 entries isn't sexy, right? So we want something else. But here's what we can do. Take this out. Now, remember I said your source can be HDFS, right? So here's the version how you can do reading from HDFS. Now, this boring stuff over here, it's the job configuration, again, where you define, what is your path for your source, which is a folder named books in my, my class path. And this is your output path. And this is your input format, output format. You tell to Hazelcast how to parse this as it reads from HDFS. And then, but that's the key, again, this is exact same code, distribute stream dot from source. This is your HDFS with this job config. And that's how you map the key value that is you receive there. You take the string value of those. And then from that, you do the same collect to IMAP. The key is going to be a, sorry, this is a copy basically. What this does is takes the same thing from HDFS and Aziz copies it to map, but the only thing is the key, I receive it as a string from HDFS, but I convert that to the long as a line ID. And the value is basically the same. And let me, and I could do actually print source here just to show you how it looks like when I do that. Again, this is on my local machine, so it's going to just use my local file system as HDFS, but hopefully you got the idea. So I have multiple books on my file system, so it created multiple threads, loaded those books into IMAP, and my print limits it to 100 so that we don't go crazy here. So this is what the print looks like. So I'm printing all the lines that I read from these books, right? And this is not sorted, this is just any 100 lines. But you got the idea. So I'm loading from HDFS now to my map, right, with the 2 lines of code basically. And then I want to do, as I load this is my result map. I want to call the distributed with this result map. So I want to do word count on these actual books, right? And if I execute this, I think we are running out of time, but I'll try to be quick. Again, the same thing. We are loading the data, and so this is the load part, and then we are doing the word count part. And as you guess, I didn't have any my uninterested words or anything like that to limit them or to filter them out. But I got the apparently it goes the most commonly used word, and some other boring words here. I could do a limit there, but I'm kind of not liking this one. So which is the empty space. So I want to limit that out. So let's do this. While I'm doing a word count, I want to go and I want to say that as I do flat map, I want to do filter. No. I want to do filter the words that are not empty. Yeah. So I filtered out the empty ones now. So if I execute the same thing one more time, hopefully we shouldn't see that empty space there. There you go. Yeah. Okay. Now, I want to go back to my presentation and really quickly show one more thing. So far, everything that I executed was batching, right? We had a file either in data either in Hazelcast or HDFS, and we did some processing. We had a finite result, right? Well, how about streaming? So JET again supports the streaming, and it supports for the items that can you might want to join 2 streams, and items might be coming out of order. And and we support the out of order windowing using the watermarks, and we have fixed windows, sliding windows, or sessions where it can time out. And an example could be let's read from a Kafka as messages comes, and let's say write them to Hazelcast. So that's going to be my example here. I have one more. cursor. So here's an example. Now, this one right now uses the core DAG API, okay? So it doesn't use the pipeline API. Java 8 Stream API isn't available for streaming anyways. And here's how it looks like. So I create a Kafka cluster. It's just a local Kafka, embedded in this JVM. And I create a separate thread that will go and continuously fill the topics of this into this. Basically, will send into two topics of Kafka, T1 and T2, and keys are just integer as they increase. The value is just integers as they increment. And I'm publishing them into the Kafka continuously, right, nonstop. And so that's my, stream of items. And over here, I have JET. I start a JET. This is like an extra node here. So I basically start two nodes of JET. So, it will be a little bit interesting. And I create my DAG. And now this is, again, we are going a little bit lower level API here. But some properties that my Kafka processor will need, I set them up. But basically, it's a very simple DAG. I have a vertex source, which is Kafka. I have a sink, which is a write to another Hazelcast map. This is the name of the map. And I, join these two. So basically, a small program that will continuously read from Kafka and write to Hazelcast map, right? And that's that's what I'm trying to do. And then I execute this DAG here. I basically submit the DAG, and then I have a kind of a log operation that continuously I print the size of the map as it grows, right? So let's go and execute this guy here now. Let's try to create the Kafka. So yeah. So first, it took a while for JET to start and the process to start. But as my Kafka submits messages to topic, in the meantime, in parallel, JET is receiving them from Kafka. Of course, I didn't set up any JVM parameters. It's going to go out of memory soon as it stores the generated items into the map. But basically, a small program, a simple program. You have a source from Kafka. You are basically continuously loading the results for the map, and you could do again, some windowing, grouping by, and all that's more exciting stuff other than just copying them as is. Yeah, it's going out of memory. Okay. That's all. And we are right at 5 o'clock, a little bit over time. But any questions?
So, the jobs are running, there is anything to monitor the jobs that are completed?
So we are working on that. As I said, this is a new project, so we are working on integration with the Hazelcast Management Center, or a slightly different monitoring tool to monitor the jobs and, as you said, those stuff. Project is a little bit on early stages, like the pipeline API is just introduced in 0.5, and the HTF reading from HTFS is introduced on the late. I mean, we did have HTFS, but as a core API, part of like Java to Stream API, it's added lately. And fault tolerance actually is on the latest version. Again, still snapshot version, but it's going to be released very soon. So not yet, but definitely on the to-do list to add monitoring. So the idea is, specifically for the people who are familiar with in-memory data grids, with Hazelcast, with others, add the compute power right away to them, and then eventually, of course, grow the audience for a lot of other use cases. And again, we could have read from Kafka right to HDFS, right? That necessarily has nothing to do with Hazelcast. And maybe do some aggregation and store the aggregation in Hazelcast map so that your application can consume it from there, but the actual data might be in HDFS, and this allows you to do that. So not the easiest tool out there, probably in terms of the API, will require you to a little bit go through the documentation and look into the examples, but it's really powerful. We did some performance benchmarks, specifically with as your window sizes grows, other tools like Flink and Spark their performance can exponentially increase. Whereas with JET, the way we implemented it for a lot of use cases has a very consistent latency. Specifically with Stream, as the end of the window appears, you want to get the result of the aggregation of that window right away. Let's say if we are doing, look into my pace in the last mile, right? So the moment my mile is over, I want to get the computation of it right away, right? So with Hazelcast JET, it's much faster compared to Flink or Spark, where they have to, at the end of the window, they have to do one by one aggregation, whereas Hazelcast will keep the aggregated results and will just apply them as the items arrive. And when the window is over, the result will be available and over. So stuff like that. I mean, there's been a lot of engineering going in to make sure that these things are fast and as efficient as possible. Yeah, so that's our jet.hazelcast.org is our community website, and we have a Google group where we can discuss things, and we do discuss things. So I appreciate any feedback. Thanks for listening. Have a great evening. Yeah, sure. One more. Yeah.
So this streams run on partition thread or?
No, it has its own thread system. It doesn't use Hazelcast internal threads. Yeah, it just uses Hazelcast for clustering, basically. Yeah.
So this looks like a library type of stuff. It's not like something you had to set up like this, set up read first and then start reading stuff to it.
You could, yes. So I didn't show that because Greg's presentation had some of those stuff. So JET could be working with embedded Hazelcast that's on that JVM. So everything we stored was, like on that JVM, right? Maybe think of a Spark. Spark itself is not a storage, but
You use it embedded, then you only run on one bus, one JVM.
no, multiple. It could be multiple JVMs. Yeah. But still, Hazelcast is embedded in all of them, right? Both of them are distributed systems, so you could embed that. But JET also can work on a distributed on a remote Hazelcast as well. So you could have my client application where you submit your JET jobs, but the Hazelcast could be on a remote cluster. JET itself could be on a remote cluster. I didn't want to go into those deployment complexities here, but everything could be here a client. So you could have your JET cluster running separately and your Hazelcast cluster running separately, and you submit the task. Yeah, and of course then it's a little bit less interesting because for this JET to consume the data, it needs to read them from Hazelcast. But if you have the data embedded, or Hazelcast embedded inside the JET node on the cluster, that gives you the power of, while you process, I can just make use of the local data, right? As I go, I'll just use the data that is stored locally to me to make it fast. Does that make sense?
So if in the case distributed environment, like you will have to kind of like deploy in every node of them.
Yes.
And then start them go up, and they are all like together.
Yes, and they will form a cluster, and they will, yeah.
And
Yeah.
then you basically a client.
Yes, exactly. So the code here would look like, so actually if you, I think on the pipeline API I had not example, but like I can show you the interface. So the, say the pipeline API, for example, you can say like this sources, it can be, see here, can be read map, and then can be read remote map. See, so like instead of reading from a local map, you could say read from a remote map. That is, and the client config will give you how to access that remote Hazelcast cluster to read from that map. So you can have all different topologies here. But of course, you get the most advantage with having them, next to each other. Yeah. Any other question? Okay, appreciate it. Thank you.